Yeah, do we have challenges concerning the assignments? All right. I will add more assignments to it today and I will share it as Google link. Maybe that'll be better. So, last week we were able to look at some implications of some prepositions. We were able to look at some prepositions around the consumer theory. So we also look at how some of the implication. You have a question? All right. So we also look at some of the implications or some of the prepositions that surround the Wallachian demand. So we said one of the most important one is this function is always homogeneous and is of degree 0. So there are situations of degree 1, okay? We'll see that as we proceed. But this is of degree 0, so it's homogeneous. So, and I also explain what that meant. So you can go through the video of the other class. So I proved some theories here. So now I will add it up with this beautiful exercise. So this class today, we'll look at the implications, the economic implications of the Weierstrass demand theory. All right, how it affects individual. So remember, we talked about the weak axiom that of this actually have greater effects on has some properties that relate to weak axiom of review preference. Yeah, so and we also verify that process before we gave this assignment, and we asked you to verify this assignment, all right, to show that if this behavior of these goods are inconsistent, just to show. So, and also to show if one of the either of the groups is of review preference, okay, or vice versa. So today we want to look at the implications, all right, the implications of the weak axiom. So some of the major implication of the weak axiom is the wealth effect and the price effect. So the major one is the price effect and the weight effect. So, or we call it the substitution effect. So these are the major implications of the weak axiom. All right. So, and in this class, we're going to consider so many examples. So, when we talk about remember what the weak axiom is saying that if a certain goods, there is certain price. So we have a new price. Let's say this is X P of W, the old price. So, and we have P prime W prime as a new price. So now the new price, the product of the new price and the old price, if is satisfy the Wallachian demand, yeah, then the new price, the old price and the new demand, all right, will not be affordable. We exceed the price, the weight, the previous or the initial weight. So that is what the weak axiom of the weak axiom is saying. So anytime we have that, we said it satisfy the weak axiom. That means if one goose is not affordable when we are having a new goose. So then if such happen, it satisfies the Wallachian demand. Otherwise, it violates it. All right. So now, when we are given some of the implication we want to look at here is that how these prices or how these changes affect this rate of substitution. Rate of substitution is saying how consumer make choices between different commodity. All right. So so if we so by the time we look at this, so when we have change in weight is simply telling us that we are taking the difference between the initial weight and the new weight. That is W prime minus W. So the difference is denoted by this change in weight. Also change in price. This change in price. So is saying that we are taking the new price from the previous price. All right. So why the goods remain the same? That is what they're saying. So at the same goods, so the change in price. So then you can say as we denote it as delta P is like P prime minus P. So and this effect, so this weight effect is known as the Slutsky weight compensation. Definitely. So this is just an illustration to prove, to want to describe or to prove the Slutsky weight effect. So then assume we have this which satisfies the Waras law. By the Waras law, we know what that means. This is the Waras law. So for the new price, all right, with an initial demand, definitely the change in price will be of this form. So we can replace this delta P by its corresponding P prime minus P, and we have this. So this is the new goods, all right? The new goods minus the previous goods, the change in it. So this is nothing but delta P. So we can write this as delta P, then this is change in X because the new goods minus the previous goods. So, and that is delta X, all right? So under a condition that the new goods or the new demand correspondence is not the same as the previous demand correspondence. So it's not equal. So anytime we have that adjustment in wealth, we will have the product of price and wealth to be less or equals to zero. So we try to make a proof for this. So the proof is kind of lengthy, but let me just explain some of the proofs so you get it better. So initially, we prove it in two ways. So we prove it under two conditions, all right? The first condition is we assume that the demand correspondence are different. So the new demand and the previous demand, we assume they are different. And the second condition we're going to use is that we assume that what the demands are not uh, different. All right. So these are the two ways. So the weak assume implies holding for all compensated price change. So these are the two ways we prove it. So by the time we do that, we take this to the other side of the equals to because we assume that these are not equals to zero. So but in this first case, we assume it's zero. The second case, we assume it's not equal to zero. Yeah. So here, if we assume that they are equal, then this we can take it to the other side. So then if this becomes the new price minus zero, we assume it is zero. Then you have the change in price minus this guy. So definitely we have the change in price there. This is the change in demand, just like we saw earlier. Then we can factorize out this, all right? So, or we expand it. This P prime multiplied by this, the entire demand will give us this. Then or this P multiply with the entire demand will give us this price, all right? So that is what we have. At the end of the day, uh, we recall this is from the weak assumption, right? So This was the weak assumption, the first weak assumption that says the new price and the previous goods or the initial goods must be equal to the new weight, right? Then it means that the product of the previous price and the new goods will not be affordable. So, but the Wallace law tells us that the weight is equal to the price times the demand. Alright, that's Wallace law. So, if we logically combine this together, we're going to have something like this. So, we're just subtracting this from this. Alright, so W prime minus W prime will give us 0. Then you have this P common to both sides. You factorize it out, then you have this equation. So that's the first leg of the equation of the proof. Then you take the other side of it. So where we assume that if the weak assumption is not satisfied, whenever our goods are not the same, so definitely we still follow similar process. But remember, this one will be the second side of the weak assumption theory that says it's not affordable. Remember the weak assumption theory? Let me look if I still have that definition here. Yeah. So this is the weak assumption theory. So it says that this is what this if this occurs, definitely the new price and the old price is not affordable, must exceed this. All right. So that is the weak assumption. So that is exactly what we are using to prove the other side. So, and at the end of the day, yeah. So that's why we have this inequality here. All right, that's why we have this inequality. So by the time we subtract these two from each other as well, so we'll have similar thing like this. Yeah, we have something like this. All right, so and we'll compare this equation and the previous equation, which is equal to 0. So we arrive at uh, something like this. So at the end of the day, so yeah, we're going to have our change in weight to be the product of the change in price and the so this is a case where we are using the differentials. Yeah, remember initially this was like change in price. Yeah, so like change in price. So this is change in exchange. So if we consider a differential case, if the prices are differentiable, that means they are continuous. All right. So definitely we'll have it to be in this form. So that is that. Any questions so far? This is just a proof. So uh, the differential form. So this differential form can be expanded to be of this form. Remember, this is the x. The x is telling us that the change in price. Any question? All right. So the x is telling us change in the commodity or change in demand. So with respect to price. So this is the change in demand, all right, with respect to price. Remember that our change in our demand is a function of what? A function of weight and price. So we're going to take a partial derivative at this point. So this is a partial derivative with respect to price while holding price constant. Then you also differentiate with respect to weight while holding uh, weight constant. So this is what we have. And don't forget that what is our weight from this equation? You look at here, the weight, the change in weight is like the product of to change in weight is the product to change in weight is the product of our price and the demand correspondence. So we can substitute it in this place. So by the time we substitute it here, this is what we have. So, and by the time we make factorization, we can factorize change in P here. We also factorize change in P here. Definitely we have this. Yeah, so we have this. And this is nothing but, so we can write this in a matrix form. So this is change in price of this certain commodity, this product, and this is change in weight of this corresponding to this product, the demand, the transpose of the demand. Yeah, so we have it. So by the time we factorize out our change in P, we have it here, and this is nothing but the Slutsky equation, which can be represented in the Slutsky matrix. So, and this matrix is called this substitution effect, or the Slutsky matrix. Yeah. So all of these are just differentials of the Slutsky equation, or the Slutsky equation. Yeah. So remember, this is the equation. So this is change in price with respect to change in weight. Then this is change in price. So these are for different. These are units of each of these demand functions. Yeah. So what these are the units. So it's an L by L matrix. That means there are L multiples demand in L multiples uh, weight. Yeah, that is what we have there. So let's consider some examples. So I hope we record this example in the last class. So in the last class, we only consider the case where we are asked to uh, check if this L dimensional goods satisfy homogeneity, right? So, and we were able to achieve that in the previous class. So today, the question that is associated with this question now is to check, or is to compute the substitution matrix. Yeah, that means the Slutsky matrix for this equation. How are we going to compute this? So we are given that whenever P is having this value 1, 1, 1, and the weight is 1. So, and also a constant function of beta is also 1. We want to show that this uh, this equation is we can compute this Lusky matrix from it. The matrix I showed earlier. So this matrix, so we can compute a matrix like this from all of these demands. Remember, these are three demands, all right? So can anyone explain how we computed, or how we show that this demand function is homogeneous in the last class? Can I have anybody? If you can still recall how we get that done. Yeah? Halimotion, mic is on. Please can put it off. I hope my screen is visible.
Yes, it is.
All right.
Sorry, are you saying anything? Hello?
Hello, sir. We're not seeing anything.
Maybe he's having an issue with his network.
Yeah, I think so too. I think so.
No, please. Can you hear me?
Can hear you now. We can hear you. Go ahead, sir.
Oh, sorry, my network went off and still trying to fix it though. So, why I take us through the basis of how to differentiate. All right, so that's why I'm showing this. So, how do we differentiate a function? So, we must be familiar with that concept because in this section we often going to be using that. So let's say we are given a function. So we want to differentiate. This is a partial derivative. There are two types of differentiation, either partial or total differentiation. All right, in a partial differentiation, so we use the Cayley day like we've seen earlier. So if we are given this function, this is x1, so it has two functions, p and w. It could be multiple functions, okay? It could be p1, it could be p2, p3, and w. All right. So this has two functions, p and w, and we are differentiating with respect to what? With p1. All right, meaning that w will be held constant. All right. What I meant by constant is that just like we have it as a number, when you differentiate a constant according to the rule, it is zero. So any time you differentiate that, it goes to zero, right? So when you differentiate p, you reduce it. So that is differentiation. So in this case, we have a function. All right. Don't forget our x1. Our x1 is a function of two different functions that has numerator and denominator. So then this type of function is called a quotient. All right. So we're going to apply the quotient differentiation. So if this does not have numerator and denominator, we're going to use either a product. If they are product of two variables, remember these are p and w, so we're going to apply the product rule, but this has the product at the numerator and also another functions at the denominator. So we're going to apply the quotient rule because it has numerator and denominator. All right, so that's why we're applying a quotient rule. And the quotient rule says that anytime you are differentiating using the quotient rule, so this is it in the form of f of x is equals to g of x and h of x. G of x is a function, h of x is another function. So in this case, you differentiate g by holding h constant, just like we have it. You can say this is g prime. G prime means you differentiated g. Then h is held constant. We did not differentiate it. Also, hold g constant, this numerator, hold it constant, it's h. All right. Then the denominator, you should square it. So you should have h square. So this is just the way of doing it. Then you can just perform some little algebra here or arithmetics and you have your final result. So that is how to differentiate such function if it's in the form of a rational function, numerator and denominator. All right, so we apply the quotient rule. So our function x1 has that form, the numerator and the denominator. All right, so how do we differentiate this? So let me write. So like I've explained, here we have the numerator and the denominator. This is our function. So we differentiate it. So we can say let g be this numerator, which is what? P2 and W. And let our h be the denominator, which is. So therefore, by the time we differentiate G of W, which is P2 and W, meaning that we should hold P2, differentiate the other. All right, hold this. So that's the principle. So by the law, what we are saying is that differentiate G partially with respect to P1 by holding H constant minus, remember, don't forget this minus, it's always there, minus G, holding G constant, differentiating H with respect to P1. All right. So why am I using P1? Remember, there are three P's there in the question. We have P1, P2, P3. So we're going to differentiate this each for P1, P2, and P3 as well. So that we can have our Slotsky. So therefore, we have the H, differentiate H holding G constant, and you take H square. All right. So, and when you take H square, it means that P1, P2, P3 will all be squared. All right. So, and when you differentiate P2, holding this constant, so you have W here. So let me differentiate that. Yeah, so this is the differentiation. All right. So from this first one, when you differentiate your G with respect to P2, all right, we have W left. Then this is our H, right? So that's our H. Then also, when you differentiate H, so when you differentiate H, you have P1, P2, P3. You hold P2W, which is our G, you hold this, then you differentiate your H with respect to P2. Error there, and P3. Let me fix that. Yeah, so you differentiate that. This is what you're going to have. P1, so you're going to have, with respect to P2, you're going to have P1 and P3 left. All right, so as a constant. So the denominator, you squared it. Yeah, so by the time you remember, we are given that this is P1, P2, P3. So P1 is 1, P2 is 1, P3 is this. All right, so definitely our weight is 1. Weight is 1, and you have P2 to be 1 and P and W to be 1. So you have here to be 1. All right, so here you're going to have P1, P2, and P3. So yeah, that's what you're going to have. Oh, still an error here. This P1, P2. Yeah, that's correct earlier. P2, yeah. So this is what you're going to have. So the P1, P2, P3 can be factorized, and it's clear the other p in the denominator. So yeah, it's clear the other one in the denominator. Therefore, you have P1, P2, P3 left in the denominator. By the time you substitute 1, 2, 1 here, 1 here, 1 here, so that will give us minus 1 over 3. So that will be the differential for x1, P1, all right? So you can also do that for x2, x3 as well, too. When you do that for x2, x3, so now let me quickly recall the Slutsky matrix. So here is our Slutsky matrix. All right. So by the time after we are done with the computation here, so that will give us minus 1 over 3 here. So if you do the same thing for x2, you're going to get 1. If you do the same thing for x3, you're going to get 0 in your x3, because this function here, remember, this is just only x2 here. Don't forget p2 in the numerator. By the time you can differentiate it with respect to x3, that will give us 0 here. All right, and the other hand there, it's what? 0. So, and you count that 0. So also you take the other function, x2. You take x2, you also differentiate it using the. So you differentiate x2 with this same process, you're going to have, and substitute those values, you're going to have 0, minus 1 over 3, and 1 over 3. By the time you take x3 as well, this function, you differentiate this with respect to p1, you differentiate with respect to p3, 1 over 3, 0, and minus 1 over 3. So this is the Slutsky matrix, or the substitution effects of these demands. Remember, these are demand correspondent. X1, X2, X3 are the demand correspondents. So that is how to derive the substitution. Any question? So let me quickly show another example. This is a very good example. So this will give us some clarity about, yeah. So this is another example. So show that if this is a demand function, a Walrancian demand function, then
It's like network is really disturbing the instructor today.
Sorry for the break in transmission. Having a hectic network issue here. I guess I have fixed it once again. So I hope I'm audible.
You are audible. You are audible. Well, are you saying anything? Can you hear me?
Yes.
I don't know. But you can see the screen. I don't know if you're saying anything.
You said that thing, but I don't know.
You said?
I said the thing was showing, but has gone off. I guess it's his network. Yes.
hope I'm audible.
Yes, you are.
So sorry for the break of transmissions once again. We're on my network tonight. So that is how to show this. So that's just a simple proof of the Lorentzian demand function. So whenever we want to show is of degree 0. So now I have another example here again. So this example is also very important. Please help I'm audible, please.
Yes, you are.
Thank you. So here's another uh, example also. So we are given this question. So we have to consider a commodity goods. Let's say 3 commodity space. So that's what we are given. And we have to show that this function, this function x1, which is equals to minus p1 plus p2, x2 is equals to minus p. So we have to show that this function, satisfy. Okay, we are told that this function satisfy homogeneity of degree 0. I hope by now we should be able to prove that easily. So we can verify that on our one and also satisfy the loss of demand. We should be able to do that as well. Maybe I'll give us that. But let's look at how it satisfies homogeneity. All you just need to do is to substitute alpha in place of p, alpha in place of w. Remember, alpha is just a positive number, so greater than 0. So by the time you substitute it here, you substitute it here also. So you'll be having alpha p1 or minus alpha p1 plus alpha p2. Then you can factorize that alpha. Then remember it's of degree 0. So alpha to the power of 0 is what? Is 1. Definitely we'll still have this function back, which is still x1 of pw. The same thing with p2. So every linear function, satisfies homogeneity of degree 0. Yeah. So the same thing we have here. So that is just how to prove homogeneity. But we are asked to also show that the Walras law is satisfied. So how do we do that? So how do we show that the Walras law is satisfying? So for us to do that, we'll just quickly recall the Walras law. But this is not my concern tonight. I'm not looking for the Walras law, but the questions ask us to show the Slutsky. Yeah. So, show that this demand also satisfies the Wilkinson and demonstrates that its substitution effect matrix. So that we just find the substitution matrix from this question, but we can always show that this satisfies homogeneity and the Walras law. For us to show the Walras law, all we just need to do is use p to multiply both sides, alright? Use p to multiply here, I'm going to have what? Use p to multiply here, I'm going to have what? By then you add both of them together, alright? So I'm going to be what? So we can also find Slutsky equations from here. So we're using the differential method. So when we differentiate this, so this is what we want to compute the matrix itself. So that's what we want to compute, this matrix itself. the first approach to do this, so the first approach is to get a differential, to get each of the differential of x1. So when you differentiate x1 with respect to p1, remember we are not having three values there, so this can be reduced to what? 2 value. The matrix can be reduced to 2 by 2 matrix and not 3 by 3 matrix. So let me quickly reduce it to 2 by 2 matrix. So let's say we want to reduce that to a 2 by 2 matrix. So if we want to reduce that to a 2 by 2 matrix, so we're going to have something like this. Yeah, so this will be the 2 by 2 matrix of this. This will be the 2 by 2 matrix. So you're having the first demand, the second demand, third, and the fourth. So meaning that we are going to take 4 derivatives in this case. So let's quickly take the derivatives. So it differentiates x with respect to p of p1. So you're going to have minus 1, right? So and that is how we got this minus 1 here. So when you differentiate this function with respect to p2, which should give us 1. That means the x1 with respect to p2 will give us 1. And that is how we got this 1 here. So similarly, we have the x2 with respect to minus p1. So we differentiate this with respect to minus p1, we're going to have minus 1. So, sorry for that, we're going to have minus 1. So let me correct that. So you're going to have minus 1. So this is the minus 1. So this is how to compute the Stokes matrix. Yeah. This is how to compute the Stokes matrix of any demand function that is given. So one of the properties of this Stokes matrix is that it's negative semi-definite. So I believe in your mathematics, you should have been talking about a semi-definite matrix by now. So, but if you have not done that, you will get to know as you proceed. So a semi-definite matrix is a matrix if the first entry is negative. You can see the first entry here is negative. So, and you take the determinant. The determinant of this minor, or of the first minor, will be what? Will be positive. So negative, positive, negative, positive in that order. So that's a negative definite matrix. So it's a semi-definite if it is always positive. There is no zeros there. By the time you take the determinant. So if you take the determinant of this matrix now, you discover that this will be like 1, right? Because 0 times 1 is 0, minus this will give me minus 1 times 1, give me minus 1 times minus, will give me positive 1. So the first entry here is negative, that's the first minor, and the matrix itself, the determinant of this matrix is what? Is positive. So negative, positive, negative, positive. So there is no case we can have 0 there. So that means it's always positive. You say it's a negative semi-definite matrix. So if you look at the one we computed earlier here, so if you look at the first minor is what? Negative, right? The first minor here is negative. Then if you take the determinant of this matrix, you discover that is what? So look at the first minor here. So this is also positive because minus times minus will give me plus minus 0. So this minor here, this minus 1, 1, 0, and minus 1 is also positive. So we're going to have negative, positive, negative, positive, all true if you compute. So we're going to have about 9 minus here. So each of the cases, we're going to have negative, positive, all true. So this is a good property of a Stokes matrix that is always negative semi-definite. All right. So any questions so far? Is there any question? Can I ask a question? Mr. Ahmed, do you have a question?
I came into the class late.
Oh,
So if I ask question, I might be taking us from the first part where you started from. I was trapped in the elevator for
Oh.
like 40 minutes before I got out of that place.
oh, sorry
You
about
can
that.
continue. I'll go through the video.
All right.
Okay. Yeah.
So what we are considering tonight is just the implications of the Wallacean law or the weak axiom, some of the implications of the weak axiom. So we say it has two major implications, which is the weight effect and the price effect. So, and the price effect is generally known as the substitution effect. So we can classify everything as the substitution effect. So at the rate at which a particular commodity is being substituted for another, if either price goes up or price comes down. So the rate of substitution between this. So that's why you can see that we're having two prices and two uh, weights here. So we're having two commodities, X1, X2, yeah, and many more like that. So these are just what we are considering tonight, the implications of the weak axioms. So here is another good example. So you can find one example here. So this example says we should, yeah, good. So we are given a 3 economic goods. So L is equal to 3. That means we can find it in the consumption set of Harrow tuple. So suppose that the demand function is of this form. So we are given a demand function, all right? So let's look at how we can compute a Slutsky equation, the Slutsky matrix. So let's look at how we can compute the Slutsky matrix. Yeah, so here is the question. To consider this economic goods of 3 dimensions, which is of this form: x1 is equals to p2 all over p3, x2 is equals to minus p1 all over p3, and w x3 is w all over p3. We know what w means, right? W is the weight, p3 is the price for goods 3. So these are 3 different prices, one weight. The weights remain constant or remain the same or true. Then we have 3 demands. So these are 3 demands we have. So remember, the demand is a function of weight and price. All right. So we want to show that. So the question asks us to show that if this function is homogeneous of degree 0 and satisfy the Wallace law, we also show that this function violates the weak axiom, and we should also show that any function, inverse function, V is standing as an inverse function, multiplied by the Slutsky matrix must be equal to 0, either from the left or from the right. So these are some good properties of a Slutsky matrix. But before we can compute this third one, remember, you must compute your what? Slutsky matrix. So that's why I have shown us how to compute a Slutsky matrix in the last 2 examples. So now let's quickly look at how to check. I don't need to solve how to check for this demand anymore, or if it is homogeneous. So all you just need to do, take an alpha and substitute in place of P. Take an alpha, substitute in place of W, right? Then you have alpha P2 here all over alpha P3. So by the time you factorize that alpha completely, alpha to the power of 0, alpha to the power of 0, those one will give us 1, and we have P2 over P3 back. So you can see this first one will still give us X1 PLW back. Similarly, you do the same thing for this also. So this just becomes a negative alpha P1 all over what? Negative alpha P3. So you factorize that to your alpha, then alpha can cancel out, or you take it to the alpha to the degree of 0, alpha to the degree of 0. So they go, and you have x2 back. Similarly, do the same thing for this. So showing that this is homogeneous is quite easy. So I don't know if you have problem in checking homogeneity of a function. If you do, please just call my attention. So let me, okay, I think I have the solution here. Let me quickly look at and compute the solution. Yeah. So now here is the solution. So just the solution is, consider this as consumer goods. So suppose that we have this demand given. So now to show for homogeneity, yeah. So this is what you just need to do, just like I've explained. So you have alpha here, you have alpha here. So you can factorize out the alpha. So this take alpha to the degree of 0 and becomes 1. So it gives us the question back. So this is just what I've just explained earlier. All right. So let me quickly look at how we can show that it satisfies the Walras law. So yeah, for the Walras law, so this is what we're going to have for the Walras law. So remember the Walras law says I should take P, my price. I should use my price to multiply my demand. All right. I should use, there is a linear combination of all price. All right. From according to the budget line, we have the budget line equation where we have P1 times X1 plus P2 times X2 is equals to W. Remember that? So that's the budget line. So that's exactly the budget line equation. That's what we are applying here. So we have X1, P1 times X1, so which is the demand function we have for us of X1, then P2 X2, and P3 X3. Okay, so and now we have P1. You have a question? All right. So now if you look at P1, P2 very well, so we discovered that P1, if you substitute P1, X1 into this equation, so you just be having P1 all over P2 all over P3. So we have minus. Remember, this other one is negative. Yeah. So this negative one. So this is the negative one. So by substituting this value in place of x2. So you substitute it. So you have P2, x2, and x2 is negative P1 over P3. So that's how we come about this. Plus then this by P3. All right. So we are using the Walras law to multiply the demand that we have. So this is W P, P3 over P3. So by the time you look at this very well, P3 we cancel out this, then these are the same. All right, this is P1 P2 over P3. So this is P1 P2 over P3. We take their differences, it turns 0. So this and this cancel out, I left with weight. So it means that anytime I use price to multiply weight, to multiply my demand, it gives weight. So definitely we have the weight. So that is, we have shown that it satisfies the Walras law. So anytime I have a question, I ask you to show that this satisfies the Walras law. Just use your price to multiply your demand. Just ensure you're going to get weight. So as you get your weight, you've shown that easily. To show homogeneity, take alpha and substitute into the demand function that you have. Check if we have the demand function back. If you can achieve that, you've shown that. So let's look at if this violates the Wickers. All right. I've shown earlier how we can figure or how we can prove it, right? In the example 2 or thereabout. So I showed how we can prove that demand, how we can show if a demand function satisfy the weak axiom. All right. So from this example, I think, yeah, I showed if a demand function of these types satisfy this. So these are just the procedure. All right. So you just record the Walras law and the weak axiom uh, order. So by the time you get that, so but if you want to prove its contradiction, its violation, it's very easy. All you just need to do, you can just think of numbers or think of any physical substance that you can use to uh, make such manipulation and achieve something that is contrary to what we have. All right. Remember, the question says it satisfies the weak axiom. All right. So I think, yeah, this satisfies the weak axiom. So we need to show violation. That's why we have this question. So to show violation, what we just need to do is to think of numbers, or you can use numbers or find some principle that you can use to make that manipulation to show that you have a result that is contrary to the question. So when you can do that, you show a violation. Remember when we are dealing with violation of the weak axiom in the preference, you saw how we did that. So when it does not satisfy transitivity, then we can prove its violation. So let's look at how we can also do that here. So in this case, I use numbers to show its violations. All right. So so let's let p let let us have this type of price, which is 1, 2, and 1, and our weight should be equals to 1, and also price should be of 1, 1, 1, and our weight should, that is P1, P2, P3. That's what this means. All right. But we're having three prices here: P1, P2, yeah, and P3. So we have three prices here, right? So that's why I'm using a three dimensional list. All right. So then this is my weight. So these are two different weights. Remember, the law of weak axiom says that when we have a new weight, there are two weights involved: the initial weight and the compensated weight. All right. So in the compensated weight, this is my compensated weight. All right. So this is the initial weight. All right. So this is my initial price. This is my compensated price changes. All right. So I pick this two. So I will now substitute this value into the weak axiom formula, and let's see how that violates. Yeah. So now this is my new demand. All right. This will be my new demand for the first one. So I have 2 here. Yeah. Then for the price change, we have 1, -1, and the 2. Yeah. So we have that. Then when we take the product of these two, remember the weak axiom says if I use my initial price to multiply my new price, then I should have my other weights. So by the time we multiply this together, so we can check 1 times 2, all right, which will give me 2. This is 2 times -1, that will give us -2, that will give us 0. So 1 and 1. So that will give us what? 1. So that's how we come about this 1. Also, you check for the other one. 1 times the where's my new price here? 1 times 1, we have 1. Then -1 times -1, you have -1, they go. So then you have 2 times 1, that will give me 2. So that's how we come about 2. So you can see that the prices does not the new price is less, is greater than the this, which is contrary to what the law is saying. The law is saying that this initial price should not be affordable. This should not be affordable. I think P times this should be greater than this first one. If you remember in the law, so you can check the law of Wickerson very well. So he said this one should be greater, while this other one should be less. So we discovered that the new price and the old commodity is greater than the new price and the initial price and the new commodity or the new demand. Definitely it violates. All right. So do you have any question regarding that? Any question? All right. So let me show the C part. So the C part asks us to compute the usual matrix. The usual matrix, the Slutsky matrix. So let's see how we can compute the Slutsky matrix. Yeah. So for the Slutsky matrix, so arrange this matrix. Yeah. So we want to show that V times SP of this is Slutsky matrix times a new vector or a new price or whatsoever it is. Yeah, a new demand. Yeah, it could be a new demand. Yeah, so is equals to 0. So I want to show this. All right. So in order to show this, so first we need to differentiate our price. Don't forget. So we differentiate our x1, x2, x3. So and where is the differential? So this is x1, x2, x3. So x1, x2, x3. So these are what we have in this matrix. So you differentiate them partially. So when you differentiate when you differentiate x1, for instance, with respect to p1, you can have 0 because we don't have p1 here. All right. So when you differentiate this with respect to p2, you're going to have 1 over p. Yeah, going to be 1 over p. So you remember you're going to use the quotient rule here, holding P3, differentiate P2, which is 1, minus, you hold P3, you hold P2, you differentiate P3, all right? So, and P3 becomes P3, so you're going to be left with 1, all right? So, and you continue in that order, you do the same thing for P2, so is a 3 by 3 matrix. Yeah, 3 by 3. Then we have a 3 dimensional. Yeah, but yeah, we have P1, P2, P3. So remember, this one does not have P1, so automatically that is 0. This one does not have P2, we have 0 here. So it's a 3 by 3 matrix. So let's proceed. Yeah, so after all the computations, so this is what we're going to have as a Slutsky matrix. So you can take your time and do those calculus, all right, to get this calculus done. Then you're going to have all of this matrix. So if you look at this also, this matrix can be reduced because this is entirely what? This line is entirely 0. So this line can go. So then why, yeah, why I'm having this 1 all over P3 outside is because of this third one. Remember, this is W, right? So this is W because of this W. So we're going to differentiate this with respect to weight, right? So give us. So now this matrix can further be reduced because this line is entirely 0, so we can reduce this line and this line also. This last row, we can eliminate it. So this matrix will be reduced to a 2 by 2 matrix in this form. Yeah, so this is what the reduced form gonna looks like. So by the time you reduce this matrix, so you're going to have a 2 by 2 matrix. So you can just multiply your matrix by a vector, let's say V. We have to use V to multiply the matrix. So we're going to have something like this. So you're going to have V multiplied by S in both sides. You're going to have V. So V can be a function, don't forget, or V is always a function, a positive. Yeah. This is what you have. Questions?
I want to ask how you reduce the matrix into this 2 by 2. How did you do it? Because I was wondering if you are basing it on the 0, I think we have 0 under -1. So what happened? How did you do it?
Right. This is actually what happened. You can close this. When you close this row, remember matrix reduction. So you close this row,
Yes.
you close this row. All right, just like you want to take it minor. So we're going to have, remember, if you are taking something like a determinant, then this first one multiplied by all its minor is 0. All right.
Yes.
So this one too multiplied by all its minors as 0. So the only minor that will be left with, or that we can be left with, is this minor. All right. So we are using, what I'm using here is a column reduction. So this is a row. If you use row reduction, so this one will multiply all of this. So this is the only one that will be left. 1, remember we are doing 1 times, that's I don't know. So if I'm using this to multiply, I'm not using this first one, right, to multiply the entire matrix. So I'm using this one now. So I'm using this minor. I can do the row, yeah, from the bottom or from the under, right? So we're having this multiplied by this minor, this multiplied by this minor will give me 0, and this 1 multiplied by this minor. Okay, close this row, close this row. Okay, no, that does not work. Okay. So, but the column matrix, let me look if I can design that is quickly. So it's given us. So that's one way of looking at it. If you're using the column reduction, you're going to have something like this. But if you're not using that, definitely you can, when you have a row matrix that is entirely 0, this row can go away, right? So an entire row that is 0, so it can be neglected. So that is one way of doing this. then this other row, why we neglect it, or why I'm not making use of this, we can also look it in this direction. That's okay. Uh, Let me reduce this matrix so you can see something. It's going to take a lot of time to compute the minus. It's going to take a lot of time. So, but what I actually did here was to cross out the last row. Okay, I cross out the last row, I cross out this row, and I consider this minor. So that I actually did. But if I want to reduce it to 9, it's going to take a lot of time. So I don't know if you get it clearly, or I should explain it more.
So I was expecting to see that, okay, this is the rule of what you do to reduce the matrix to what it looks like now. There's this spelled out rule on how to do it. That was what I was expecting. You understand?
Yeah. So one of the rule is that if you're having a row that is 0, all right, it's you can remove that row completely from the matrix. All right.
Okay.
That is a
Yeah.
rule in matrix reduction. So another why so this other one, this why I remove this last row is this. Remember this row is gone, right? So I'm having a uh 2
By
by
three
3 matrix, right? So
matrix. Yeah.
now I'm having a 2 by 3 matrix. Now I want to take its minor, all right? I'm taking its minor. So the only minor that will favor this a semi-definite matrix is can't remove this upper minor, okay? Which is a 1 minus 1. I can't remove it. If I should remove it, it's no longer a negative semi-definite, because a negative semi-definite will always start with a negative uh, minor. So this will be the first minor I should have. So I have to let this bottom one to go. So which is 0 and 1. So that is my aim. But naturally, if you are having a row with zeros, you can cross it out. So or if you perform a column reduction here, so a column reduction here, we let this row go. That is the bottom row and this last row. So this bottom row is adding no value to this entire matrix. So that is it. So if I want to perform this column reduction right now, how we arrive at this finally, but it's going to take me a lot of time because of the matrix I'll be constructing. So I will maybe I will state that out explicitly and send it in before the next class, or in the next class I'll present the entire breakdown. I don't know if it's clear.
Okay. It's fine.
So let's proceed. So why we have uh so we are okay, something is missing here. Yeah. So why we have v multiplied by the Slowski. All right. So why we multiply this either from the left or from the right. So we can also multiply this from the left or from the right. So v1 is v here is just a tuple of vectors. Don't forget. So which can be v1, v2, v, and if we should expand that further and perform some operation on that matrix, we're going to have it to entirely be 0. So just like this can turn to V1. Yeah. Sorry, I want to compute this. Yeah. So one should be in form of a transpose. Yeah. Yeah, I think I got it. Yeah. Something is still missing. Okay, actually I should be having V1, V2. Yeah. Not V1, V2, V3. Because I've let the last row go. Yeah, this is what we should be having. Yeah, by the time we multiply by V, remember our V is a vector of order 2 now. So this is what we should be having. So by the time we multiply these vectors, all right, we're going to have this entire matrix to be 0. So that is what we're going to have. So let me know how to do vector multiplication. So this will just be like V2, right? So this will be V. Then this will be V2 squared, V2 squared. Yeah. So if you compute this matrix completely, you're going to have 0. Any question? So if no further question, let me put down my screen. So and do some summary. So that is all we have for. This is all I have for you tonight. Yeah. Okay, if you look at all these examples here. So this is just the last example we consider. So here is the complete question. So this is all I have for you tonight, and this is the end of the second chapter. So in the next chapter, we'll be looking at some classical problems on. So we're going to look at some utility functions here. We're going to look at utility functions that are around the Cox-Douglas equations here. So that's what we'll be looking at in the next
Please,
question.
where's the attendance, please? Hello, is Halima there? You can post the attendance.
Alright. She's not. She's not online.
There's no attendance for today.
Alright. I don't know if she posted it in the chat, but no, she did not. But don't worry, I'll take note of that. Well, I guess someone has taken note already. Someone has taken note already. So, but you can send it like request. Okay. So far so good. Please, if you have any questions, either from the beginning, let's use the next 10 minutes to wrap up those silly questions before the next tutorial. Remember this Friday, next week Friday will be tutorial for micro, right? So if you have any questions so far, you can ask or let's settle it before the tutorial. Or yeah, this assignment. Let me quickly give us the solution to this assignment. Yeah, it was part of my agenda tonight. This exercise. Did you attempt it?
Supposed to submit it.
Yes.
Kai.
Okay, don't worry. I have a lot of questions, all right? So, beautiful questions. Let me give out the solution to this. The solution is easy. We are to show that if this behavior is consistent, all right? So, it's very easy. You know, we have price here. This is our supply, or this is our the quantity demanded. This is the price, all right, for each year. So, this is the price, this is the quantity, this is the price, and this is the quantity demanded. So, but this price is missing, but this quantity is missing. So, but this price is known. So, we're going to apply the law of demand. Remember the law of demand? So, which which is in line with the weak axiom because we want to show that it has some it has some relation with the weak axiom. All right, so meaning that we're going to use the law of the weak axiom, which says if one goose is preferred, this is the law of the weak axiom. Yeah, this is it. So we're going to do price of 1 year times the quantity of that year plus we have 2 years in this table. Every 2 years in this table. So price of 1 year times the quantity of that year plus price of the other year times the quantity of the other year must be less or equal to the price of this year times this plus this. So by the time you solve this equation you have for the first one, then you do the other other side. All right. So let me quickly share my other screen if I have that solution there. Yeah, we have the attendance in the chat box. All right. You can quickly fill that while I share my other screen. Yeah, good. Yeah. Yeah. Is my screen visible?
Yes, it is visible.
All right. Thank you. So let me quickly run through the solution for that. The solutions are quite Shots. They are shots. Yeah. So let me quickly look at this. Yeah. So we assume that weak assumption is satisfied, then this consumer, his behavior violates the weak assumption. Alright. Then if that holds, just like I've explained, you have this price of this year to multiply to fix something here. Yeah. So you have the price. So you have the price of this quantity, all right, of the price of this year to multiply, okay, of year two to multiply this, right? So let me call this as y, this question mark. Let me replace this quantity by y, all right? So I sum this year two to be less than this first year, all right? So you can also do it otherwise, the way you are convenient with. So you can say 100 times this price, which is this, plus 100 times this price, which is this, all right? So when you sum this together, then you also do the same thing for the year two, right? So you show that they are equal. 120 times 100 as the price times quantity. We are just applying the law, right? So this will give us the weight, all right? So this will be the weight. So this is the demand, price and demand. So that is the law we are applying here. You have question?
Yes.
Do.
So I can see 100 times 120 plus this 100 times y. Where does that 100 times y come from? Is it not supposed to be 80 times
80
y?
times y, yeah. It ought to be that. That is um, yeah. So this is for the other side. No, I think we are correct with this. The new price, all right? The new price, this is the, remember we are using the, let me quickly type this formula. Let me type the formula that we are using. This is new price P prime of P Yeah, we are using a formula that looks like this. All right. So we are using a formula that looks like this. P prime, that means the new price. All right. So times old quantity. So this is a formula I use is less than weight. So this is a formula that we are using here. So this is P, the price, all right, times the old quantity. That's all right. So price of new quantity, new price, which is 100. Okay. So we are using the price of year 2 to multiply that of goods 1. So this is absolutely correct. So we are using price of year 2 to multiply the quantity of goods for year 1 or for year 2. So the quantity of goods here is 120 and the quantity of goods here is 100. I don't know if it's clear. For goods 1, the two goods are 120 and 100. Am I still on? Yeah. So that's correct. So the goods here is 120 and 100. So that is what we have there. So that's how we come about 100 and 120 here. They are the goods. So these are uh, the price here is 100. So that is correct. Price is 100. The new price is 100. Why the old goods? All right. Why the old goods is 120 and why? Yeah, these are the goods for year 2 or the new goods for the year 2, 120 and why. Then for the initial prices, the price remain 100. So then for the other one, the goods are what? 100. So the goods is the price is 80. All right, the price is 80, but the goods is what? 120 and 100 respectively. So that is so by the time you solve this very well, you're going to have something that looks like this. You're going to have y to be between 75 and 80. All right, so that's what you're going to have. Then by the time, so you can see that y is between 75 and 80. So meaning that it violates the behavior is not consistent. We don't have a particular value for y. So value ranges between 75 and 100. So we can't really figure out a particular value for y. So that's not a consistent behavior. So that one is that about that. Then if you look at the B parts, which says you should check if the bundles, the B parts, say the bundle in year 1 is refer to year 2. All right. So how do we handle that? So to handle that, we're going to just consider the first equation in the same way. Something is still missing here. Yeah. Yeah, we're going to consider this equation where it is greater than. All right, so by the time you solve this equation alongside with this first one, so you're going to achieve y to be 75. 75? Yeah, y should be less than 75. Then for the third one, we want to check if the bundle of in year 1 is revealed, of year 2 is revealed preferred to year 1. So you still follow the same order, but when you change the inequality here, so I'll make this complete solution available if I'm sending the notes. Yeah. So this is just the solution. So this is just solution for the other one. So let's call it a day from at this junction. Any question? Any question before we call it a day?
No question from my end.
All right, thank you very much. So I'll make this solution also available for study so that when my assignment comes on Wednesday, you have a complete assignment by Wednesday. So you should have a lot of basis to guide you. So thank you all, and thanks for your time. Good evening once again.
Thank you and good night. And please, you update the folder for this course for us so that the whole of the materials will be completed. Thank you.
Yeah.